The famous phrase, "one small step for a man, one giant leap for mankind," has echoed through history for more than half a century. It has been over 50 years since humans first set foot on the moon in 1969. The Apollo 11 mission not only marked a historic milestone in space exploration, but also became a symbol of America's victory in the space race against the Soviet Union. However, the race to the moon never truly ended. After decades of relative silence, Earth's natural satellite has once again become a major focus of space exploration programs. The difference this time is that the competition is no longer limited to two superpowers. Numerous nations and private organizations are working toward the goal of returning humans to the lunar surface. But why has the moon become so important again? To understand that, we need to go back to the era of World War II and learn about an extraordinary figure. Wernher von Braun ronduplelikende plaatsrollie, Germany's V2 rocket program. In 1944, the V2 became one of the first rockets to reach altitudes beyond the boundary commonly recognized as the edge of space. His engineering talent quickly attracted the attention of both the United States and the Soviet Union as World War II came to an end. Both countries recognized that rocket technology would be crucial, not only for military purposes but also for future space exploration efforts. The United States gained an early advantage by bringing von Braun and many other German scientists to America through Operation Paperclip. This group of experts later made significant contributions to the development of the nation's rocket capabilities. Von Braun eventually became one of the leading figures in the U.S. space program. His experience with heavy-lift rockets proved essential in the development of the Saturn V, the launch vehicle that carried American astronauts to the moon. By the 1960s, the United States and the Soviet Union had entered an unprecedented rivalry. Every achievement in space was viewed as evidence of a nation's scientific strength, technological capability, and organizational power. The Soviet Union achieved a series of remarkable milestones, sending Yuri Gagarin into space as the first human to orbit Earth, conducting the first spacewalk, launching the first woman into space, and laying the foundation for future space stations. The United States responded by accelerating its own efforts. The competition reached its peak when the Apollo program successfully landed a total of 12 American astronauts on the moon. Yet after these extraordinary achievements, the momentum behind the race began to fade. Once many of the political objectives had been achieved, it became increasingly difficult to justify the enormous costs of space programs. NASA's budget reached exceptionally high levels during the 1960s but gradually declined afterward, as the rivalry between the United States and the Soviet Union became less intense. Spending vast sums on crewed lunar missions became harder to defend from both economic and political perspectives. As a result, humans largely stopped returning to the moon for decades. Following Apollo 17 in 1972, lunar exploration shifted primarily toward robotic spacecraft and unmanned missions, but another factor also transformed the way humanity explores space: computer technology. Consider the first generation iPhone, introduced by Apple in 2007. It contained just 128 megabytes of RAM, a modest amount by today's standards. Even so, that memory capacity far exceeded the capabilities of the guidance computer used during Apollo 11. The Apollo guidance computer had only about 4 kilobytes of RAM, and its hardware was significantly larger and heavier than the electronic devices we use every day. This comparison highlights the astonishing pace of progress in computing technology over the past several decades. Today, computers help power self-driving vehicles, control aircraft, analyze massive amounts of data, and operate highly sophisticated spacecraft systems. As a result, robots can perform many space-related tasks with a level of precision and endurance that humans often cannot match in hazardous environments. This is one of the key Reasons why space agencies have increasingly focused on unmanned missions. Instead of sending astronauts into extremely dangerous environments, scientists can deploy robotic explorers to distant destinations to collect data, capture images, analyze surfaces, and carry out tasks that humans are not yet able to perform directly. Comet exploration missions provide a perfect example. Rather than sending people to a distant and dangerous celestial object, robotic probes can accomplish the mission at a fraction of the cost and risk. The Moon underwent a similar transition. After 1972, humans temporarily withdrew from the lunar surface, while robotic spacecraft continued exploring it on our behalf. Today, however, the situation is beginning to change. It is not only a symbol of victory anymore. It could become an important stepping stone for journeys farther into space, especially missions to Mars. Therefore, the 21st century moon race could look very different from the competition between the United States and the Soviet Union in the past. If the first race was primarily about demonstrating national power, the new race may pursue a much greater goal, building a longer-and experimentis time. The question may no longer simply be who will be the first to set foot on the moon. Instead, it could become who will build the long-term future of humanity beyond Earth. Beyond technological limitations, enormous costs were also one of the major reasons countries eventually stopped maintaining crewed missions to the moon. NASA's Apollo program cost approximately $26 billion in the dollars of that era, equivalent to hundreds of billions of dollars in today's money. This was an enormous investment in a program whose original objectives were not purely scientific, but were also closely tied to the geopolitical competition between Washington and Moscow. To understand the difference, consider India's Chandrayaan-3 mission. In 2023, the South Asian nation's lander successfully touched down near the moon's south pole at a publicly reported cost of only about $75 million. This enormous gap demonstrates how robots can significantly reduce the cost of space exploration. They do not require life support systems, do not need to ensure the safety of astronauts, and do not have to bring human beings safely back to Earth. Autonomous spacecraft can carry out dangerous missions at a fraction of the cost, but money is only part of the story. The space race during the Cold War was heavily political from the very beginning. Washington wanted to demonstrate the superiority of the Western model, while Moscow sought to show the world the technological strength of the Soviet Union. As a result, the goal of sending humans to the moon did not arise solely from the need for scientific research. One noteworthy detail is that among the 12 American astronauts who have walked on the lunar surface, Harrison Schmitt was the only one with direct scientific expertise in geology. Most of the others were selected from military pilots or test pilots. This partly reflected the Apollo program's primary at the time, when in the race onset the United States had achieved its most important goal and the Soviet Union was no longer a direct competitor in the race to send humans to the moon. The political motivation quickly declined, but the deeper reason came down to a very simple question. What would humanity gain by continuing to return to the moon? Consider the history of ocean voyages centuries ago. Explorers such as Christopher Columbus and Ferdinand Magellan opened new routes and revealed new lands to Europe. But exploration was only the beginning. For people to return, establish or maintain a long-term presence, those territories had to offer something of significant value. That value could come in the form of gold and silver, natural resources, trade routes, strategic military positions, or some other economic benefit. If a territory offered little meaningful value, it would be extremely difficult to convince governments to continue investing enormous resources to maintain a presence there. For decades, the moon was viewed in much the same way. The rock and soil samples brought back to Earth by Apollo astronauts helped humanity better understand the moon's geological history and formation. However, in the prevailing view of the time, the moon appeared to be little more than a barren cold world with limited practical value. That conclusion gradually reduced the appeal of lunar research among political leaders, but science did not stand still. Advances in analytical technology allowed researchers to examine old lunar samples using methods that scientists in the 1960s and 1970s could not have used. Over the years, the picture of the moon began to change. One person who played a particularly important role in this process was Harrison Schmitt, a member of the last crewed American mission to land on the moon to date, unlike most of the earlier Apollo astronauts. Schmitt received extensive training in geology. Before his flight, he helped train astronauts to observe lunar terrain and collect geological samples on the moon during Apollo 17. He personally conducted geological research on the lunar surface and brought back numerous important rock samples to Earth. These samples helped scientists gain a better understanding of the moon's chemical composition and geological history. Further research revealed that the moon contains many elements that could be valuable to industry, including silicon, aluminum, titanium, and various other minerals. On Earth, these elements are typically extracted from deposits deep underground and then subjected to multiple processing stages to separate them from impurities on the moon. However, the distribution of materials has some very different characteristics. This has gradually turned the idea of extracting extraterrestrial resources into a serious subject of scientific research and space strategy. One name that frequently appears in these discussions, helium-3, is a rare isotope of helium on Earth, but it is believed to exist in significant quantities within the moon's surface soil and rocks. Helium-3 has been proposed as a potential fuel source for future fusion power systems. However, overly optimistic claims should be treated with caution. Fusion technology based on helium-3 has not yet become a practical commercial solution. While extracting and transporting resources from the moon back to Earth would require entirely new technologies, nevertheless, another discovery far more practical has significantly changed the game. Water at the beginning of the 21st century. NASA's robotic missions, including LCROSS and the Lunar Reconnaissance Orbiter, provided important evidence that water exists as ice in certain regions of the moon. The most significant areas are near the lunar South Pole, in some deep craters. The terrain prevents sunlight from ever reaching the bottom directly. These regions can remain extremely cold for very long periods, creating conditions that allow water ice to survive. This discovery is far more significant than simply finding a source of water. If humans can extract water directly on the moon, this resource could serve many purposes, providing drinking water, producing oxygen, and even generating hydrogen and oxygen for rocket fuel. In other words, the moon could become a natural refueling station for journeys farther into the solar system. That is when the moon began to take on an entirely new meaning, rather than being merely a place to plant a flag and demonstrate national power. The moon could become a research base, a resource extraction hub, and a stepping stone for missions to Mars. A new competition has therefore begun to take shape, with particular attention focused on the lunar South Pole. If the space race of the 1960s was primarily about prestige and political superiority, today's competition is also tied to economics, resources, technology, and future strategic influence. The moon may contain raw materials that could prove useful to the space industry. More importantly, controlling strategically advantageous locations could provide a major advantage to countries seeking to establish long-term operations beyond Earth. So far, the number of countries that have successfully carried out soft landings on the moon remains very limited. The Soviet Union, the United States, China, India, and Japan have achieved important milestones through different programs. Among the emerging competitors, China is particularly noteworthy. China entered the era of human spaceflight relatively late. In 2003, Yang Liwei became the first Chinese citizen to travel into space aboard the Shenzhou 5 spacecraft. Since then, however, Beijing's space program has developed at a remarkable pace. China has progressively built its capabilities in satellite launches, developed crewed spacecraft, completed its own space station, and común particulars. The change program has enabled China to achieve a series of major milestones in lunar exploration. What is especially notable is that Beijing does not appear to want merely a one-time presence on the Moon. Its long-term objective appears to be building the capability to operate routinely beyond Earth, and if that becomes a reality, the 21st century moon race will no longer simply be a competition over who gets there first, it will become a competition over who can stay longer, use lunar resources more efficiently, and turn the moon into a stepping stone for the next era of space exploration. In 2013, China reached an important milestone when the Change 3 spacecraft delivered the U-2 rover to the lunar surface. It was China's first successful robotic lunar landing and marked the first soft landing on the moon by any country in decades. 6 years later, Beijing attracted international attention again with Change 4 in 2019. The U-2 rover was deployed to the far side of the moon, often referred to as the dark side. It was the first time a human-made spacecraft had successfully landed in this particularly difficult-to-reach region. Then, in 2020, the Change program achieved another major milestone. The Change 5 spacecraft collected lunar samples and returned them to Earth. It was the first time in decades that humanity had received newly collected lunar rock and soil samples since the Soviet Union's Lunar 24 mission in 1976. These successive achievements demonstrated that China was not merely seeking to participate in the space race but was building a long-term space program. One of Beijing's biggest goals is to land Chinese astronauts on the moon before 2030. Looking further ahead, China aims to develop the capability to operate regularly on the lunar surface, including plans to cooperate with Russia and other partners on the development of the International Lunar Research Station. The region receiving particular attention is the lunar South Pole, where scientists believe reserves of water ice may exist inside permanently shadowed craters. While China has continued to achieve new milestones, the United States' effort to return to the moon has also faced numerous challenges and delays. NASA made an important advance with Artemis 1 in 2022. The Orion spacecraft completed an uncrewed flight around the moon, testing critical systems needed for future crewed missions. Under the original plan, Artemis 2 would carry astronauts on a flight around the moon. Artemis 3 lunar surface, with a particular focus on the South Polar region. However, the program's schedule has been revised several times. Technical, safety, lunar lander, and equipment-related issues have pushed the timeline further back than originally planned. The competition between the United States and China is also not limited to the lunar surface. An increasingly important area is cislunar space, the region of space between Earth and the Moon. Within this region are 5 special locations known as Lagrange points, designated L1 through L5. At these locations, the interaction between the gravitational forces of celestial bodies and orbital motion creates favorable conditions for spacecraft to maintain a relatively stable position, while consuming less fuel than many conventional orbital trajectories would require within the Earth-Moon system. Some Lagrange points could serve as strategic locations for future communications, observation, and transportation networks. In particular, the region near L2 is important for communications with the far side of the Moon because this side of the Moon always faces away from Earth. Spacecraft operating there cannot communicate directly with ground stations without a relay satellite. China recognized the importance of this early on. In 2018, the Qiqiao relay satellite was placed in a suitable position to support communications for the Change 4 mission. With this system, China was able to maintain communication with the lander and rover operating on the far side of the moon by 2024. Beijing launched Kuiqiao-2, a new generation relay satellite designed to support China's subsequent lunar exploration missions. Systems like these could become an essential part of future space infrastructure, particularly as countries begin deploying more spacecraft, research stations, and transportation vehicles around the moon. The United States does not want to be left out of this competition either. Through the Artemis program, Washington is building an international network of cooperation involving numerous countries. One of the key foundations of this strategy is the Artemis Accords, introduced in 2020 to establish principles for peaceful, transparent, and responsible exploration and use of outer space. An increasing number of countries have joined the initiative, including Japan, the United Kingdom, Australia, the United Arab Emirates, and many others. The alliance's goal is not simply to return humans to the moon. Washington aims to create a broad ecosystem of cooperation encompassing scientific research, technological development, infrastructure construction, and preparation for missions farther into space. China, by contrast, has showed path and has not joined its accords. Step. Competition between the two superpowers an increasingly significant geopolitical dimension. In reality, the current race has gone far beyond the question of who will set foot on the moon first. The moon could become the first stepping stone toward a new space economy. Frontiere. Humanity could develop the technologies needed for missions to Mars and even farther into the solar system. The country that establishes launch systems, bases, communication networks, resource extraction technologies, and long-term operational experience on the moon first could gain a significant advantage in the next phase of space exploration. For now, the United States still holds a very strong position thanks to its technological foundation, historical experience, and extensive network of international partners. China is rapidly narrowing the gap with a program that has been implemented with considerable consistency. It is difficult to determine with certainty which side will achieve all of its objectives first. In fact, the most likely scenario may not be that only one country emerges victorious. Both the United States and China could eventually have a presence on the moon, and that is precisely what makes the future so fascinating. Imagine that one day, American and Chinese research bases are both established near the moon's south pole. Separated at that point in, the moon would no longer be a distant world seen only in photographs taken by robotic probes. It could become the site of the first great power competition, beyond Earth, a competition in which tensions that already exist on our home planet could be reflected on an entirely new world. And if that happens, the moon's south pole could become one of the most strategically important locations of the 21st century. If you enjoyed the video, please hit the like button, subscribe to the channel, and share your thoughts in the comments below. Thank you, and I'll see you in the next video.